Hello and welcome. This is Dr. Schleif with another paper one worked example. As you can tell by that sound, we're dealing with momentum conservation before and after the collision. We've got two objects, X and Y, in an isolated system that undergo a perfectly elastic collision. Right away, perfectly elastic collision, let's use that to review. In a perfectly elastic collision, the initial kinetic energy equals the final kinetic energy. In any collision, perfectly elastic or perfectly inelastic or somewhat inelastic, in all collisions, the initial momentum equals the final momentum. Previously, and if you click on the link above, you can see where we've combined these ideas to arrive at a simpler way to approach questions that are perfectly elastic. And that is that the relative speed of approach will equal the relative speed of separation. So how fast the objects see each other before the collision will equal how fast the objects see each other after the collision. In order to calculate relative speed, the rule is if the objects go in the same direction, you subtract their speeds. If the objects go in opposite directions, you add their speeds. And so because these are both going to the right, 20 minus 12 equals 8 meters per second. Objects X and Y see each other at 8 meters per second before the collision. Because it's perfectly elastic, they're going to see each other at 8 meters per second after the collision. If you try 2 meters per second for V, you find that 10 minus 2 is indeed 8 meters per second. We also find that we get a relative speed of separation by using choice B. 18 minus 10 also gives an answer of 8. So both A and B sort of mathematically solve the correct relative speed of separation. Choices C and D we could discard as obviously incorrect. So the question becomes, well, which one of these velocities is the correct one for Y? And if you just sort of connect this with some common sense, if an object crashes in to this object, it's going to speed it up, not slow it down. So because object Y is initially going at 12, we would expect that its velocity would increase when a faster moving object crashes into it. And so we would discard choice A is incorrect because there the velocity is slowing down in favor of the correct answer, choice B, 18 meters per second. Both is faster than the initial velocity and the relative speed of separation equals the relative speed of approach, which is true with a perfectly elastic collision. This is Dr. Schleif, still live in the physics life, and may the fourth be with you. Always.